So let's do a little comparison shopping right here. We've really gone over problems like this first one in the last video. That is, we could certainly see how these two functions right here could be said to be a substitution, where we have an inner function of x squared plus 1 and a derivative of 2x dx, but we have a very similar function, but somehow different with this. How are they alike? How are they different? Well, of course, in the first case, when we take an integral of a quantity like 2x times x squared plus 1 to the fourth dx, we're treating it as x squared plus 1 to the fourth times 2x dx, and we can certainly see that if we make a substitution where u is equal to x squared plus 1, well, then almost certainly du is going to replace 2x, the derivative of x squared plus 1 times dx in the differential form. So in this substitution, we're taking the integral of u to the fourth du, when we know what's going to happen right there. Now let's compare this to what's happening in our second integral. And in their second integral, we have a very similar situation, except the problem's slightly different, right? Because we're saying we're taking an antiderivative of x squared plus 1 to the fourth. This time we could say, well, it's x times dx. But if we proceed to make u equal to x squared plus 1, just as in the last case, we would find that du is equal to 2 times x dx. We've only got 1x times dx. What to do? Well, you guessed it, right? We can just take this constant of 1/2 and multiply it as divide it as 1/2 to the other side, and just make 1/2 of du equal to x dx. Clearly, this is going to be a constant that we're going to replace, and we'll end up with an integral that looks more like this: 1/2 of the antiderivative of u to the fourth du this time, where we're replacing x dx with 1/2 du in the second part. All right, so we're going to come up with some very similar answers. I guess in the first case, when we take our antiderivative, we know we're going to say it's 1/5 of u to the fifth plus the constant. Whereas in the second case, it's going to be 1/2 of 1/5 u to the fifth plus our constant. So rewriting, this last term would be 1/10 of the quantity x squared plus 1 to the fifth plus c. Whereas in the first case, very similarly, making the replacement, we're only going to get 1/5 of x squared plus 1 to the fifth plus a constant. All right, so that's the similarity between these two. Actually, not too terribly bad. So we can actually generalize our method like we did over here in red to handle other integrals as well. Consider the following case. We've got sine of 3x dx. Kind of similar to an example we did before. We can certainly make u equal to 3x so that we're taking an antiderivative of a sine of u. But then we also have to handle du. So if u is equal to 3x, then du is going to be equal to 3 dx. And the only way to balance this out with our expression that we have is to make this 1/3 of du, so that we get 1 times dx, and therefore our expression here will be 1/3 of the sine of u times du. Just taking that constant out in front, of course, our antiderivative then will be 1/3 of the negative of cosine of u. Don't forget that negative sign here in this particular case, plus c. And so rewriting that one more time will give us negative 1/3 times the cosine of 3x plus our constant of integration. All right, one more that's very similar in a way. We have, in this case, u replacing the quantity 3x plus 4. Why? Well, we want to try and get an expression that looks more familiar to us, and we certainly know that if we were to take an antiderivative of e to the u, we would get e to the u. But of course, we also have to take the derivative of u, which means that we're going to deal with du equal to 3/4 of dx. Well, we only have dx, so that means, well, of course, we're going to move this constant over by division, giving us 4/3 times du, replacing dx. And so in our method right here, this is going to become 4/3 times e to the u du, and we know that the integral right here is going to be 4/3 of e to the u plus our constant, and making that replacement one more time right here for u, our expression for which we would take a derivative, we could verify we're going to get e to the 3x over 4 dx, is going to be 4/3 e to the 3x over 4 plus a constant.